All right, part 5. So we're talking about the ideal gas laws here. If we're talking about number 5, we got to start by reading the text. So take a moment to go ahead and read that, and then we'll go over the answers. So what is the ideal gas law? According to the text, it's right there, right up front. It's a mathematical relationship between pressure, volume, number of moles of substance, temperature of the gas. This formula that represents it is PV equals nRT. That is definitely something you're going to want to remember. Kind of rolls off the tongue, PV nRT anyway. You won't have to do actual calculations with it, but the relationships that it represents are super important. So what is a mole? Again, it's right there in the text. It is a number. It is a standard of measurement. It is a number of something. Think of it similar to terms like a pair or a dozen. This is a review from chemistry. The numerical value of a mole, instead of representing like 12 like a dozen does, it's 6.02 times 10 to the 23rd particles. That is a really large number, but it's the way that we measure the amount of substances on an atomic scale. Now, this last 3 parts of the text is kind of summarized by this table. I had initially recorded myself going through this, but someone called in the middle of that recording, and I didn't realize that it had stopped it, so I'm going to have to go back over it. These relationships that are talked about here are going to be illustrated here in this table. So what we've done is we've taken isolated variables. You'll know that notice that there are multiple of them, and left just our variables of interest. So these are the variables that we want to see the relationships between, and these are the key relationships for the PV and RT formula. So let's start with pressure and volume. You'll notice that they're multiplied by one another, which means an indirect relationship. For pressure and time, they're divided, which is direct, and then for temperature, and then temperature and volume, you'll notice that they're also divided by one another, which is a direct relationship. So let's go through these problems that talk about these relationships or get us to apply them. So if we're increasing the temperature, what will that do to the volume of the gas? Well, because we know that they're a direct relationship, as illustrated right here, increasing temperature will lead to an increase in volume. You've actually experienced this before if you've ever bought balloons in the middle of winter. When you buy balloons and you go outside, you're decreasing the temperature. And if you've ever brought them outside, you'll notice they kind of like shrivel up. That's a decrease in the volume of the gas that it takes up. So that is a direct application of that. You've seen that before. And then for number 2, decreasing the volume of the gas will do what to the pressure of the gas? That's talking about this relationship. It's an indirect relationship. So decreasing our volume will increase the pressure. And you can think about this if you had a box with, let's say, 4 molecules inside of it. They're all moving around. They have a certain amount of kinetic energy. They're bouncing around. Now, if you decrease the size of that box with the same kinetic energy, they have less space to bounce. They're going to bounce into one another more, hitting more, causing more force to build up, increasing the pressure. So none of these are too revolutionary. We should be able to see these play out pretty straightforward.